Okay, let's get started. Let me first take roll. Donnelly is here. Levengood is here. Miller, Neff, Norberg, Sheffield, Sullivan, and Tillis. All right. What's your last name? Huh? Oh, shoot. You know something? That's a lab. Okay. I'm sorry about that. Let me start again. Okay, Bartram, Blair, Donnelly's here. Elwell, Levengood is here. Miller, Sheffield, Sullivan, Tillis. All right. Okay, so as I recall, there's just one more topic remaining in chapter 4 before we move on to chapter 5. And it has to do with what you can see on the screen right now. It has to do with metals as reducing agents. So we talked about redox reactions, and just to give you a brief review, redox stands for reduction oxidation. Something is reduced when it gains electrons from something which is being oxidized, and vice versa. Something is being oxidized when it gives up electrons to whatever is being reduced, all right? And what you're looking at here on the screen is what is oftentimes referred to as a activity series, right? Which is basically a series listed in a particular order of metals, listed in a particular order in terms of their reducing strength, all right? The higher you go in the series, the greater would be the reduction strength of the particular element. Hydrogen is included in this series, particularly because of the fact that we can apply the principles based on this series when it comes to reactions between metals and acids, such as this one right here, all right? So I'm going to explain, and you probably should have met this before in your introductory chemistry, but basically this is used when it comes to what we call single replacement reactions. So if you have, let's say, let's say, hypothetical reaction AB reacting with C, then you're going to get, in this particular type of reaction, AC plus B. So this is what we call a single displacement reaction, where the C displaces or replaces B and ends up being combined with A, all right? And then B is produced as a byproduct of this reaction. Most of these reactions, in fact, I can't think of any examples of exceptions. So I'm going to venture out and say all of these reactions are redox reactions, all right? Where you're going to observe that A undergoes, no, not A, I'm sorry. B undergoes, let me erase this here, I'm sorry about that. Basically, in this particular type of reaction, B undergoes reduction, right? And C undergoes oxidation, all right? And we're going to see some examples of this shortly, all right? So the question now becomes, how can we predict such a reaction? If you're given, let's say, a compound AB and you add C to it, will this reaction take place? And that's where this activity series comes into play, all right? So basically, the general rule of thumb is, oh gosh, okay, let me erase all of that so you guys can see that. So basically, the rule of thumb is that a metal will displace from a solution the ions of any metal that lies below it in the series, all right? So basically what they're saying here is that if you have a metal being added to a solution which contains a metallic ion, then if that metal that you're adding is above the metallic ion in the series, then displacement will occur, all right? And the example that is given here is the fact that zinc will displace hydrogen. Now, as I said before, hydrogen is included, even though it's not a metal in this series, precisely because of reactions like these. So if you look at where zinc is here in this series, and if you look at where hydrogen is, which is right here, then basically zinc, based on this series, you can make a prediction that zinc will displace hydrogen when you add zinc to a solution which contains hydrogen ions. And that's exactly what happens. If you take a piece of zinc and add it to acid, in fact, for those of you enrolled in my lab, you're going to see that reaction at work, where in the very last stage, zinc is actually added, or actually, wait a minute, no. Well, it's a similar reaction. Zinc will be added to a solution containing copper ions and thereby displacing the copper, all right? So that's basically what happens in these reactions. So basically you can use this to help you to make predictions as to whether or not a particular reaction will occur. Let me just give you one example, which you can use this series. You can use this series. Okay, what did I just do? Okay, you can use this series to predict that a particular reaction will not take place. And the example I'm going to use here is Cu plus HCl. So the question is, will that reaction occur? All right, so you see that copper is right here, all right? And this is where hydrogen is. Copper is below hydrogen, right? So because copper is below hydrogen in this series, then basically we can say that this reaction will not occur. So NR, no reaction, will occur in this particular case, all right? So that's basically how we use the activity series to make such predictions. Okay, one last thing here. This here, what you're looking at here is basically some pictures showing you a type of titration reaction or titration process, which is called redox titration. So you should be now familiar with acid-base titration, where you can use the concentration of, let's say, an acid to determine the concentration of the base, or vice versa, when in this particular case, you would use an oxidizing agent to determine the concentration of a reducing agent. Now, I'm not sure exactly what are the reactants in this particular case. I suspect very strongly that at least one of them is potassium permanganate, which would be in the burette. Potassium permanganate has a distinctive color of purple, all right? And then this could be some reducing agent. It could be, for example, oxalic acid or some other reagent that will react with the potassium permanganate, which would be the oxidizing agent. And basically the whole process is very similar to what you'd have done in titration, where you add your, in this case, permanganate to your solution down here, and you look for a color change. And in this particular case, the color change would be from colorless to pink. And then you do some reading of your volume of permanganate added, and then you do some calculations, and you can do your determination of the concentration of one or the other. Unfortunately, we have stopped doing this sort of reaction here at CF, primarily because the products, especially the manganese products, are very toxic, so we cannot easily dispose of them. And if we were to correctly dispose of it, we'd have to actually call a company to dispose of the waste, and that costs money. So we have just decided not to, it costs a lot of money, in fact. So we have just decided not to go ahead with doing this experiment. I'm quite sure, however, there are YouTube videos which shows you examples of redox titration. Okay, so that's basically the end of this chapter. And then what I'm going to do now is move on to chapter 5, which deals with gases. And again, a lot of what you would have meet in this particular chapter, you would have met before in your introductory chemistry courses. So gases, we all know what gases are. We know about the 3 states of matter. You have solid, liquid, and gases are a bit unique for several reasons, not the least of which is that they're very responsive to changes in volume and pressure, right? So for example, you can significantly reduce the volume of a gas easily compared to solids and liquids. It's not as easy to reduce a fixed amount of, let's say, a liquid by half, the volume by half. You cannot do that easily. Same is true for solids, but for gases, you can compress it, expand it, whatever, all right? So therefore, gases are kind of unique in that regard compared to the other 2 states of matter. Now, of course, we can explain the behavior of gases by a theory, which we're going to talk about later, known as the kinetic molecular theory. Essentially, what this theory says is that the gas, if you have in a container, actually consists of very small particles that are very energetic, always moving in straight lines, especially translational motion, we call it. And they will hit the walls of the container. And of course, if you imagine billions, literally billions of particles continually hitting the walls of the container, they will exert some force on the container, right? And that force is manifested as the pressure exerted by the gas on the inner walls of the container. Another aspect of the behavior of gases, which can be explained by this theory, is the fact that gases flow very easily and they expand to fill the entire container that they're in, right? So if I were to bring a bottle of, let's say, ammonia here, and I open it up, of course, eventually what will happen if you stay in here long enough is that all of you guys will smell it. And that's because the gas particles are very free to move around, very energetic, and therefore will tend to occupy the entire room if they're allowed to, all right? This term vapor that is oftentimes used as chemistry is more often than not refers to a particular gas which is normally a liquid under normally room temperature conditions, right? So therefore we tend to use vapor in association with substances like water, right? Water is a liquid normally, and then we would heat it to convert it to the gas, and we call that water vapor. And the same is true for methanol, right? But for other gases that exist as gases under normal conditions, we don't use the term vapor. We simply call them gases like hydrogen, helium, oxygen, and so on, all right? And another thing I want to mention here, by way of some introductory comments about gases, is that there are many low molecular molar mass molecular compounds that can exist either as gases, or if they're in a liquid state, you can easily vaporize them. You don't have to elevate the temperature too much to convert them to gases, all right? So I'm thinking of, let's say, compounds such as, well, the normal gases under normal conditions, hydrogen, oxygen, and so on. But then you have some liquids that are easily vaporizable, like, for example, acetone, all right? If I leave a bottle of acetone open here, or a beaker of acetone open here, eventually it will evaporate, all right? And therefore will become the gaseous state. Okay, so this is just a list of some gases and their common typical usage. So as you can see here, a lot of gases have applications in different areas. So for example, carbon dioxide is used in beverage carbonation. So your sodas that you drink, you know, like Sprite and Pepsi and Coke and all that, they are called carbonated beverages because basically, in addition to flavoring and all of that, it's basically a solution of carbon dioxide gas. So when these are prepared, they're prepared such that the gas carbon dioxide is under high pressure. And we're going to learn about that later on in this chapter. Henry's law comes into play, where basically the dissolution of carbon dioxide is due to the fact that the pressure of carbon dioxide above the surface of the gas in a closed system is relatively high. Once you reduce that pressure, then what will happen is that the carbon dioxide that is dissolved will start coming out of solution, and therefore it's going to bubble up and all that, all right? So we'll talk about that later on. So those are just some examples of gases. So as I said before, the kinetic molecular theory is basically the model that is used to explain all that we can observe about gases and their behavior, all right? And I talked about the fact that according to this theory, the molecules or the particles are always in continuous rapid motion, they're highly energetic, and they move in straight lines. And the term that we use for that is that we say that their movement is called translational motion. So they tend to move in straight lines. And the only reason why they might deviate from that straight line behavior is when they hit the walls of the container or when they occasionally hit each other, right? Otherwise, the movement of these particles would be straight line movement. And as a result of this understanding, then we can explain certain things that we observe about gases. So one of the things that we can explain is why is it that gases exert pressure on the inner walls of their container? And I explained that earlier. It's a continuous bombardment of the particles against the inner walls of the container, all right? And therefore, as a result of the force that's applied over a particular area, and we're going to talk about the relationship between pressure and force later on. Because of that, the gas will exert pressure on the inner walls of their container. So we can explain that particular property of gases based on the kinetic molecular theory. We can also explain the relationship between temperature and pressure based on the kinetic molecular theory. We're going to look at it in more detail, but just by way of introduction, if you think about it, it makes sense. When you increase the temperature of a gas, you're putting or imparting more energy to the gas particles. The gas particles will be moving faster. They will hit the walls of the container harder with more frequency. And therefore, the result is that there will be an increase in pressure on the inner walls of the container. All right. So that's basically a short summary of the relationship between temperature and pressure as explained by the kinetic molecular theory. So let's talk about pressure. Pressure exerted by gas, right? What is the definition of pressure? Now, pressure is one of those terms that people tend to use interchangeably with force, but they're two different things, right? Force, if you have done any physics before, force is basically a push or pull on an object. Pressure, as stated here, is the force per unit area. So it's a force that is basically exerted over a particular area. So therefore, as a result of that, and I think I have the equation here, let me see here, or I thought I did. Let me write the equation down here. So this is the mathematical relationship between pressure and force. Pressure is equal to force divided by area. Let me just check this here. Okay, so this is the relationship between pressure and force and area. Pressure is equal to force divided by area. So therefore, one can express the units of pressure in terms of the units of force and area, and the SI unit of force, as indicated here, is newtons, and the SI unit of area is meters squared. So based on those units, we can express the units of pressure as being equal to newtons per meter squared. And there's a special name given to this combination of units. It's called the Pascal, symbolized by PA, all right? And then you can, of course, have larger or smaller units expressed, but based on the prefixes used along with the metric system. The most common prefix used in association with pascals is kilo, right? Kilopascals is a very common unit that is used when it comes to expressing the pressure of a gas. But there's some other units that are used as well. And a lot of them have some historical significance, and we're going to explain why later on, but I'm just going to let you know that there's one unit known as the atmosphere unit, right? And then there's another unit known as the millimeter mercury, which is the same thing, by the way, as the torr unit. So whenever you see millimeter mercury and torr, they're both equal to each other, all right? So the next slide, I'm going to show you the relationship between the different units, and it's right here, right? So here you have 1 atmosphere on one side here, and 1 atmosphere is basically, that unit came about as a result of the atmospheric pressure that the atmosphere exerts on everything submerged in it, right? So basically, the powers of B decided that to say, well, we're going to have 1 atmosphere, and that would be equal to all these values here expressed in different units. So here we see that 1 atmosphere is equal to 760 millimeters mercury. I'll explain how we came up with this unit later on. And as I said before, because the millimeter mercury unit is the same as the torr unit, then 1 atmosphere is also equal to 760 torr. And then we have some others here. We won't be using, I don't anticipate us using this value, or this value. But here we have 1 atmosphere is equal to 101,325 newtons per meter squared. And remember, I said that the newtons per meter squared unit is the same thing as a Pascal unit. So these two are equal to each other. But this one is most commonly used, kilopascal, right? So therefore, to get from pascals to kilopascals, remember kilo means 1,000. So therefore, we divide this value by 1,000 and we get the equivalent value in kilopascals, right? So I would say for all purposes in this course, we'll be using atmosphere, millimeter mercury, torr, pascals, and kilopascals, and newtons per meter squared, all right? The others, I really don't anticipate us using those units to any degree whatsoever, all right? Okay, so let's talk about how do we measure pressure. And there are 2 instruments that are used to measure pressure. One, which we're going to discuss now, is used to measure atmospheric pressure, right? So as we all know, we are submerged in the atmosphere. The atmosphere is a mixture of gases. The main one is nitrogen, which is about 78% of the composition of the air that we breathe. And then the next most abundant element in that regard is oxygen, which is about just under 20%, if I remember correctly. And then you have some other gases like helium, krypton, well, not krypton, well, maybe krypton, I'm not sure, but other minor gases that are included as well, all right? So therefore, as a mixture, they exert pressure. And the pressure changes with weather conditions, all right? So there are instruments that have been, the instrument that we use to measure the atmospheric pressure is called the barometer, all right? So here is where we get the definition of the atmosphere unit. 1 atmosphere unit is the pressure exerted by a column of mercury exactly 760 millimeters high. I'm going to explain how that came about. So this is, again, showing you the relationship between the atmosphere unit and the millimeter mercury unit, which is the same thing as a torr unit. And then we have the kilopascal value being expressed as well, all right? Okay, so this is what we call a simple mercury barometer. So let me explain what's happening here. So we have 2 setups right here. The first setup is where we have a trough filled with this liquid mercury. And I'm going to explain the significance of this liquid earlier, or later, I should say. In this trough, we insert a tube, all right? This end of the tube is open. And what you'll find is that the mercury level inside the tube will be exactly at the same height as the mercury level outside the tube, all right? And the answer for that, or reason why that happens, is because the atmospheric pressure that is acting on the surface outside the tube is exactly equal to the atmospheric pressure exerted on the surface of the mercury inside the tube. So therefore, both mercury levels would be the same in that particular situation. All right, now what is happening on the right side is a slightly different situation where we have a tube inserted into the mercury in the trough right here, but one end is sealed. All right, one end is not opened as in the case of this setup right here. Now, the way this is actually put together is that you have your trough filled with mercury, and then you fill your tube that you're going to invert into that trough with mercury, right? And then what you're going to do now, I must say that the tube must be long enough. The tube must be longer than 760 millimeters. We're going to talk about the reason why. Well, the reason will become obvious. So once you fill that mercury, once you fill that tube with mercury, then you put your thumb over it, and you should be wearing gloves for this because you're dealing with a toxic metal, mercury. So you put your thumb over it, and then you invert it into the trough filled with mercury, and then you leave it for a while. And what will happen is that the mercury level will fall until it gets to about this height, 760 millimeters mercury, all right? Now, we can explain why that happens, because in this particular case, you still have the atmospheric pressure acting on the surface of the mercury outside. And then basically you have this mercury column right here, which is basically exerting a pressure at this point. If you think about the level equivalent to the level outside here, inside the inside the tube, what you'll conclude is that this column of mercury is exerting the same pressure at this height as the atmospheric pressure, right? So basically this height inside of the tube, the height of the mercury inside of the tube, can be used as a, let's say, a proxy for measuring the atmospheric pressure that is exerted on the surface outside the tube. So basically, if the atmospheric pressure increases here, the mercury height increases inside the tube. So you can basically use that height as a measurement. So therefore, what they have decided to do is define that 1 atmosphere, which would be the pressure that is exerted on the surface of the mercury outside of the tube, is equal to 760 millimeters of mercury inside the tube, all right? So that's basically how the mercury barometer works, okay? Now, one might be wondering, well, okay, let me not say what I was about to say. So let me quickly go through this example here. The question says, a Canadian weather report gives the atmospheric pressure as 100.2 kilopascals. And by the way, in almost all countries around the world, if you were to turn on the TV and watch the weather report, they'll be expressing the atmospheric pressure in kilopascals, while here in the States, we express it in I think is it pounds per square inch, I think, if I remember correctly. So this question is saying that what is the pressure expressed in the unit of torr? So of course, it's a simple conversion exercise, very similar to what you're accustomed to. You start off with 100.2 kilopascals, and then you have to multiply by the appropriate conversion factor. Now remember, the relationship between the torr unit and the kilopascal unit is that 760 torr is equal to 101.325 kilopascals. And that's it. All you have to do now is the number crunching. So it's 100.2 divided by 101.325. And according to my times 760. And according to my calculations, this works out to be equal to 751.6 torr. And that's it. All right. So that's basically how that is done. All right. Now, another instrument that is used to measure pressure, but this time we're not measuring the atmospheric pressure, we're measuring the pressure of a gas. So let's say you have a gas trapped in a container. You want to determine the pressure of that gas, all right? We call this instrument a manometer, all right? And basically, mercury again is used in this particular instrument, but the pressure is measured by using the difference in the heights of the mercury level or other liquid, but mercury is the liquid of choice, the best liquid of choice, between two arms of the manometer. So the manometer is a U-shaped tube, which looks like this, right? One end is closed in this particular version of the manometer, but as you're going to see later on, you can also have this end open. You're going to have your mercury in the U-shaped tube, and then one end is attached to your container, which has a gas, right? So the way this works is that you open this up, the gas flows through, exerts a pressure here, right? This mercury level goes up, and the pressure of the gas can be measured in terms of millimeters mercury by taking the height difference between the two mercury levels on both sides of the on each side of the U-shaped tube. So this height here, delta H, is basically will be reflective of the pressure that is exerted right here. And the reason why we can do that directly is because basically the pressure here is virtually zero, all right? So therefore, the height difference here is due only to the pressure that is exerted by the gas at this side right here, all right? Now, if you want to determine the pressure in terms of other units like pascals, then this equation would be the equation that you would use, right? This equation basically helps you to calculate the pressure that is exerted by a column of liquid, all right? Let me explain what these terms are. G is a constant known as the acceleration due to gravity. I don't know if you have met this before, but if you have done physics, you should be familiar with this constant. It basically measures the acceleration of any object that is falling on Earth, all right? D is the density expressed in kilograms per meters cube, and H is the height of the column, which in this case here would be delta H, right? So if G is in meters per second squared, density is in kilograms per meters cube, and H is in meters, and you plug those numbers into this equation here, well, that will give you the equivalent pressure expressed in pascals. Yes, sir?
Is G always going to be 9.8?
G is a constant, 9.8 meters per second squared, always, on Earth. If you go elsewhere, then it's going to be different, all right? Okay, so that's an equation that is used to calculate the pressure based on density of the liquid, H being the height of the liquid column, and G being the acceleration due to gravity. Okay, now let's talk about what is called the open-end manometer. The one that we saw earlier is the closed-end manometer. Okay, so again, we can use this to measure the pressure of the gas. So you're going to see two situations here. So let me concentrate on this one firstly. So again, we have the U-shaped tube, but this time this end is open, right? The other end is connected to your container with the gas. So you can imagine, again, opening this up. And then in this particular case, what happens is that the pressure of the gas will be exerted on the surface of the mercury on this side. And in this particular case, it pushes up the mercury level up to this height right here, all right? So how do we calculate the pressure of the gas based on that which we observe? Well, a couple of things you need to realize. Basically, you also have the atmospheric pressure acting on the surface right here. So this P bar here is atmospheric pressure. The reason why they put bar here is because it's also called the barometric pressure, all right? So atmospheric pressure, barometric pressure, same thing, right? So based on this observation here, clearly we can see that the pressure being exerted by the gas here is greater than the pressure that is exerted by the atmosphere on this side right here. So what does that tell us? That tells us that there's a difference in those pressures. And that difference would be given by the height difference of the mercury levels on either side of the equation, all right? Or of the setup, I should say. So basically, we can write down a quantitative relationship between the pressure exerted by the gas, the pressure exerted by the atmospheric pressure, and delta H. And that is given by this equation right here. The pressure of the gas will be equal to the barometric pressure plus delta H, right? Because delta H would be, when added to the barometric pressure at this juncture right here, would be the same as the pressure of the gas right here. So basically, as a result, we can say that the relationship between the pressure of the gas, the barometric pressure, and the height difference between the two mercury columns is given by this equation right here, all right? So that's what happens if the liquid level here is at a higher level compared to the liquid level right here. Now, on the other side, we have a situation where things are flipped around in a sense that the liquid level here is at a higher level compared to the liquid level on this side, which is open to the atmospheric pressure. So what that tells us is that the pressure exerted by the atmospheric pressure or by the atmosphere here is greater than the pressure exerted by the gas here, and the difference between those two pressures will be given by delta H. So in other words, the barometric pressure would be equal to the pressure of the gas plus delta H, and the result is this relationship right here. All right. So that's basically how we use the open-end barometer, not barometer, I'm sorry, the manometer to determine the pressure of the gas. So here's an example right here in this green box right here. It says for part B, which is over here, what is the pressure of the gas if delta H is 100 millimeters of mercury and the barometric pressure is 760 millimeters mercury? Well, all we have to do is plug those numbers into the equation that applies to that arrangement. So basically, we're trying to find the pressure of the gas. So we can rearrange this equation to get pressure of the gas is equal to the barometric pressure minus delta H. And that would be equal to, let me just do that up here. Pressure of the gas would be equal to barometric pressure, which is 760 millimeters mercury, minus 100 millimeters mercury. And the answer here would be 660 millimeters mercury. And that's it. That's how you do that calculation. All right. So that's basically how that is done. Any questions? Any questions? Any questions? No questions? I'm sorry?
I just sent present.
Okay, no problem. Okay, now let's look at this example here. And in this example, this explains why mercury is the liquid of choice and not something much cheaper like water. All right. Why do we use mercury in both the manometer and the barometer for the purposes of measuring pressure? All right. So this question says, calculate the height of a column of water, and it gives the density of water that exerts the same pressure as a column of mercury, and it gives the density of mercury 760 millimeters high. Okay, so I was recording a video when I wrote all this down, so I'm just going to use this here to explain why, to answer this question, all right? So remember, the formula I gave you earlier, which relates the pressure exerted by a column to the density and height of the column and so on. This is the equation right here. P is equal to H times G times D, right? The height of the mercury column times G, the acceleration due to gravity, times the density, right? Now, the question specifically says that the height of the water column exerts the same pressure as the column of mercury. So that's what I'm basically writing down here. The pressure exerted by the water column is equal to the pressure exerted by the mercury column, all right? Now, what I'm going to do is basically plug into this equation here, this expression for both the water and the mercury column. So for the water column, it's the height of the water column times the acceleration due to gravity times the density of water, right? That's for this side of the equation. And then for this side of the equation, I'm going to do something similar. The height of the mercury column times the acceleration due to gravity times the density of the mercury column, all right? And then to simplify things, since we have G on both sides, we can cancel them out, right? And then, since we want to find the height of the water column, I would divide both sides by the density of water. So therefore, this cancels out that, and I bring the density of water down here, and therefore I end up with this expression right here. The height of the water column is equal to the height of the mercury column times the density of the mercury divided by the density of the water, all right? And then I plug the numbers in. This is the height of the mercury column times the density of mercury, all right, divided by the density of water. And what do I get? I get this value here, 10,300, and the units here would be millimeters, all right? That would be equal to 10.3 meters, all right? And this is the reason why water is not used. Because you would need, like for example, in the case of the manometer, you would need a tube which is 10.3 meters high, right? And that would be very inconvenient, right? Just to give you an idea as to what 10.3 meters looks like, my height is just under 2 meters, right? So you would need a tube 5 times my height in order for it to function as a barometer if you're going to use water. You see what I'm saying? So that's the reason why water is not the liquid of choice when it comes to a barometer or a manometer. It's pretty much because of the high density of mercury, right? Why mercury is the liquid of choice when it comes to a manometer. So this is basically the reason why we use mercury and not something much cheaper, all right? Okay, so with that said, I'm going to get you started on assignment number 5. And okay, let me hand these out to you guys here in class. I have one for you, don't worry. Oh, you know what? I do have more. I thought And for you guys out there in Zoom, I'm going to publish assignment number 7. I'm sorry, assignment number 5 now. Let me do this. Then do this, then do this, then do this. Assignment number 7. Oh, it looked like I didn't publish 6 either. I'm sorry, not 7. I just had introductory chemistry and we're at 7 now, right? That's why my brain is stuck at 7. Assignment number 5, I'm sorry.
Did we get papers for assignment number 4?
I'm sorry?
Did we get papers for assignment number 4? I don't think so.
Oh, you didn't?
No.
All right, well, you guys should be able to. How come? All right, well, tell you what, it's published, so you can go there and do it. You can download it and print it. And if you have any questions, let me know. But you should be able to do it based on what we covered in chapter 4. All right. I didn't realize I didn't give you that one. Okay, so for you guys out there in Zoom, it's available. You can go there and print it and get started on it. And let me just say that for now, I want you to focus on questions 1 and 2 right now. All right. If you have any questions, feel free to ask. And by the way, the conversion tables for the different pressure units, you can go to, let me see here, you can go to tables and tables chemistry. And let me just show you where they're located. So they are located right here. So 760.
Yes, sir.
Okay, so what did you get? Oh, okay. Yeah, same thing. My calculator basically expresses it in scientific notation automatically. So it's 8.6. Okay, 366. So 8.68 times 10 to the minus 5. Here. I'll give you about 15 minutes to do questions 1 and 2, and then we'll resume. Yes, sir.
Okay.
Well, in this case here, because this is closed, hold on. Because this end is closed, okay, the question says, if the atmospheric pressure is 0.97 atmospheres, all right, what is the pressure of the enclosed gas in the left arm? So we're talking about this side here, right? So basically, you're going to have your gas here exerting pressure here. Because this is closed, the pressure here would be 0. So therefore, the pressure that is exerted by the gas here would be equal to the Merkel column here. So the answer here would be the same as this.
Okay.
You see what I'm saying?
Yeah, yeah, I was gonna say, if it's all closed up, it should just be.
Exactly.
sealed, you know.
Exactly. So folks, let me just say this for everybody. Let me, okay, where is that? Let me go here. Let me close this. Let me go to assignment. Okay, so assignment number, I keep saying 7.5. Okay, what is this thing? Okay, so somebody was just asking me about this one right here. You have to read the question carefully. The question says, if the atmospheric pressure is 0.975 atmospheres, what is the pressure of the enclosed gas in the left arm, which is the left arm in each case, right? So basically, in each of these cases, you have a gas trap, right? Now, in the case of the first one here, this is sealed, so there's no gas here, all right? So basically, the gas that is trapped here will exert the pressure on that surface right there, and that will push the mercury level up. Since there's no gas here, the pressure here would be 0. So therefore, basically, the pressure of the gas would be equal to the height of the mercury column, which is 45 millimeters mercury. All right? So that's what happens in the case of the first one. Now, in the case of the second one, notice what happens here. You still have your gas, which is trapped here. So that gas will exert the pressure on that surface. But now this is open, right? So now you're going to have the barometric pressure exerted on the surface on that side, all right? So my question to you is, if you remember, we saw this earlier. So my question to you is, which one has the greater pressure? The pressure of the gas trapped here, or the barometric pressure acting on the surface here? Think about it.
Yeah.
The gas, because the gas that is in this region right here is going to exert a greater pressure because it pushes up the mercury level on the other side. And the difference between these two would be the H, the difference in the mercury levels, right? So therefore, we can say that the pressure of the gas, in this case, would be equal to the barometric pressure plus the H that is measured. And the barometric pressure is 0.975 atmospheres, and the height of the mercury level is 78 millimeters mercury. Now, of course, as you all know, you cannot add those two numbers directly because they're in different units. So what does that mean? That means that you either have to convert the atmosphere to millimeters mercury, or the millimeter mercury value to atmospheres. And then you add them together, and that will give you your final answer. You see what I'm saying? So that's basically how you do that. And if you understand that one, then you should be able to do the third one. Yes, sir.
This one.
Okay, so in this case here,
Am I going in the right direction here?
let me see here. So in this case here, it's the pressure of the gas here would be,
Yeah, the barometric is stronger.
right, so you're going to be the atmospheric pressure.
So
So it should be atmospheric pressure, which is 0.975 plus the
I thought it was the minus on this part equals the pressure of the gas.
Yeah.
inside.
yeah, so the way I would express it is the pressure of the barometric pressure
Yep.
would be equal to the pressure of the gas plus the height.
Yep.
Right,
That's why I put them.
so the barometric pressure, okay, yeah, so that's correct.
All right.
So but oh, so you converted it to millimeters mercury here?
Yep.
Oh, you did that here, okay. So yeah, that looks right. Mhm.
And now would I just, can I leave that there as millimeters per mercury or? do
Yeah.
I put it in atmosphere?
No, it doesn't matter because the question didn't specify.
Sounds good.
Yeah, so the only thing I would include here is units, right?
I
that's
just
it.
want to make sure it's on the right path.
Yep. Okay, so are we finished with questions 1 and 2? Yes, sir. Okay, so this is okay. Now this here, the next line would be 0.975 minus this,
Subtract to that.
right? And then you're supposed to, oh, so you convert it from millimeters mercury to atmosphere and then you add it. Yeah, that is, yeah. But
So just subtract numbers to that.
yeah. Actually, hold on. Actually, it should be T of the gas is equal to barometric pressure plus the height. So your answer is right, but the setup is
So just
This
swap
should-
these two.
this should be yeah, you swap these two. Right. But you somehow got the right answer here. Mm. Okay, yes, ma'am. Yes, so in the case of number 3, where is it? Okay, so in the case of number 3, you're going to have the barometric pressure acting in this direction on that side. Here, you're going to have the pressure of the gas here. And because based on what you can see, you can see that the barometric pressure is equal to the pressure of the gas plus the H. So therefore, to get the pressure of the gas, that will be equal to barometric pressure minus the pressure of the gas. And then, of course, you have to make sure that both of them are in the same unit so that you can do the requisite calculation. All right? Oh, this should be, I'm sorry. This should be H. Okay, so let me move on now. Continue our discussion in this chapter. And we're going to talk about a series of laws. And again, this will be a bit of a review, so I'm going through these rather quickly. We're going to talk about the different laws which govern the behavior of gases. The first of which is Boyle's law. And as far as Boyle's law is concerned, it can be expressed in words, but it can also be expressed mathematically. So one way of expressing it in words is that for a fixed amount of gas at a constant temperature, the volume of the gas varies inversely with its pressure, right? So basically what they're saying is that if the temperature is fixed, if the amount of gas is constant, then the relationship between the pressure and the volume is an inverse proportional relationship. Another way of stating this law is that, again, for a fixed amount of gas at constant temperature, the product of the pressure and volume is constant, right? So they're both basically saying the same thing. What this law is basically saying is that the pressure multiplied the volume is equal to a constant value as long as the temperature and the amount of gas is fixed. Another way of expressing it, which is more useful when it comes to calculations, is this right here, right? The pressure, initial pressure times the initial volume of a gas is equal to the final pressure and final volume. Or I prefer to, whoops, sorry. Where is, okay, you know what? Let me do this. So personally speaking, I like to express it this way, since I'm lazy. P1 V1 is equal to P2 V2, right? Same thing. P1 and V1 would be the initial pressure and volume. P2 and V2 would be the final pressure and volume, all right? So that's basically what Boyle's law is all about. So this here shows you, let me get rid of this here. This here shows you a graphical representation of Boyle's law. The graph here to the left is a plot of pressure versus volume. And basically, as you can see, as the volume decreases for the gas, the pressure increases. So as you go from 4 volume units to 2 volume units, there is a corresponding doubling of the pressure from 1 atmospheres to 2 atmospheres. And then if you reduce the volume further by half, the pressure is doubled. So that's the inverse relationship between the pressure and the volume of a gas. Over here, we have a plot of 1 over pressure versus volume, all right? And as you can see, that's a straight line plot. And the reason why that is so is because, let me turn on my writing thing again, is because, as we said before, pressure times volume is equal to a constant according to Boyle's law, right? So if we rearrange this to get volume is equal to, how should I put this though? K times 1 over P, or if I express this as 1 over P is equal to volume over K, which is equal to 1 over K times volume, which is equal to another constant K prime times volume. All right, so let me just summarize it here. So basically it's 1 over P is equal to K prime times volume. So basically what you're doing in this graph is you're plotting 1 over P on the y-axis and a V on the x-axis, and the slope would be the K prime, all right, M. I'm quite sure you're familiar with this form of the equation. Y is equal to mx plus c, right? That's the equation for a straight line from your math courses, right? In this case, c is 0. So basically y is equal to mx would be the graph, and the slope would be given by this constant right here. So that's basically another graphical representation of Boyle's law. And for those of you enrolled in my lab, you'll have the opportunity to carry out an experiment where you actually will see how Boyle's law actually works, all right? Okay, so let me clear this again. And let me scroll down. So let me just skip all this here. Okay, so here is an example of a typical Boyle's law question. It says a helium-filled party balloon has a volume of 4.50 liters at sea level, where the atmospheric pressure is 748 torr. Assuming that the temperature remains constant, what will be the volume of the balloon when it is taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is 557 torr? So, you know, this is a typical word question where you have to pick out the essential information that you're going to need. And clearly they gave you, the volume here initially, and they gave you the initial pressure here. So this would be V1, this would be P1, and this would be P2, So remember now, P1 V1 is equal to P2 V2. The question is asking for V2. So simple algebraic rearrangement will result in that expression. And we just plug the numbers in. 748 torr multiplied by V1, which is 4.50 liters, divided by P2, which is 557 torr. And we put the numbers in our calculator. 748 times 4.5 divided by 557. And according to my calculations, whoa, is that right? Let me do this again. This doesn't look right. 748 times 4.5 divided by 557. Okay, that sounds more like it. So the answer I got here is 6.04, and the torr units will cancel out. So you're going to end up with liters as your final unit. All right. So that's basically how you do that problem. Let me just say here that when utilizing this equation, it doesn't matter what the pressure units are or what the volume units are, as long as they're the same on both sides, right? So if P1 is in atmospheres, P2 would have to be in atmospheres if you're going to use that equation. And the reason why I mentioned that is that you could get a question where P1 is in atmospheres and P2 is in kilopascals, right? So in a situation like that, you'd have to do some unit conversion. You have to either convert from atmospheres to kilopascals or vice versa. So that's something that you need to be aware of when it comes to solving problems of this type. Okay, moving along. Another law that you should have met before is known as Charles' law. And this law describes the relationship between the volume of a gas and its temperature, right? So here's the law in words. The volume of a fixed amount of gas at a constant pressure is directly proportional to its absolute temperature, meaning the temperature expressed in Kelvin. And that's very important, right? So basically what this law is saying is that the temperature has to be expressed in Kelvin in order for you to use this law to make any predictions or do any calculations. So this brings us to the concept of absolute zero, right? And this basically is referring to a theoretical idea where the temperature is so low that the gas molecules will have absolutely no kinetic energy, right? Now, I did not mention this before, but basically, when it comes to particles, there are three types of kinetic energy. You have translational energy, you have rotational energy, and you have vibrational energy, right? So if you have a gas at normal, let's say room temperature, under normal room temperature conditions, these are the three types of energies that the gas particles will have. But if you can imagine lowering the temperature such that the particles have absolutely no kinetic energy of any of these three forms, then that is considered to be what is called absolute zero, right? And this is actually where the Kelvin scale came about, right? Basically, the Kelvin scale is basically based on the assumption that if you can reach that point where the particles have no energy whatsoever or no kinetic energy whatsoever, then we call that 0 Kelvin, that temperature. We call that 0 Kelvin. And its equivalent in Celsius was determined by doing an extrapolation, right? And based on that, we say that 0 Kelvin is equal to minus 273.15 degrees Celsius, all right? So that's a relationship between the Kelvin and the Celsius value. So this is a graphical representation of what we're talking about. On the y-axis, we have volume of the gas being plotted. On the x-axis, we have temperature expressed in Celsius, right? Now, basically, if you can imagine, you lower the temperature to as low as possible, what will happen is that before you get to 0 Kelvin, for all gases that we know of, they will convert from gaseous to the liquid state before that temperature, right? In other words, you will get to the boiling point where you have the, where it will no longer be a gas if you cool it below that temperature, right? So therefore, nobody has been able to cool a gas to below that particular temperature, and it still remains a gas. So what was done actually is that, okay, you get your data points, as many data points as you can get before you get to that point where the gas liquefies, and then you extrapolate that line and see where it cuts. And what they found was that that line cuts at the temperature expressed in Celsius being equal to minus 273.15 degrees Celsius, right? So basically that is said to be equal to 0 Kelvin, all right? So that's this point right here, same thing. This would be minus 273.15 Kelvin. And therefore, as a result of that, the equation that we use to convert from Celsius to Kelvin is this equation right here. Temperature in Kelvin is equal to temperature in Celsius plus 273, and there's a combination of units here. You're going to have Kelvin divided by degrees Celsius here, all right? Oh, no. I just realized an error I made. The units don't go there. The Kelvin unit will go, whoops. The Kelvin unit will go here, but here you're gonna have Kelvin divided by degrees Celsius here. All right, so, okay, that is looking messy. Let me make it more decent. Let me just erase all this here and just correct it properly. So here, you're going to have Kelvin over degrees Celsius plus 273 Kelvin. All right, so that's the equation that is used to convert from Celsius to Kelvin. So all you have to do is plug the Celsius value here into this equation and you get your equivalent result or answer in Kelvin. All right, so that's basically how the Kelvin scale came about. All right. Okay, so let me just do this one example here and then we'll call it a day. It says a balloon indoors where the temperature is 27 degrees Celsius has a volume of 2.00 liters. Oh, by the way, I should have mentioned this before. The mathematical way of representing Charles' law is V1 over T1 is equal to V2 over T2. I forgot to mention that, right? Another way of expressing it is V over T is equal to a constant. Okay, all right. So this is the equation that we're going to use in the example I just showed you. All right. So let me scroll back to that example. So they gave you the initial temperature. So this will be T1. They gave you the initial volume, which is V1. And they gave you the final temperature. And that's T2, right? And the question is asking for V2. Right? So remember now, V1 over T1 is equal to V2 over T2. So if you want to get V2 by itself on one side of the equation, that would be V1 over T1 times T2. And then we put the numbers in. Now, remember, the Charles law specifically says that the temperature has to be expressed in Kelvin. So what we have to do in this case here is add 273 to 27, and that gives us 300. So that will be 300 Kelvin here. And we add 273 to minus 23. And this would be 250 Kelvin. All right. So we put the numbers in. V1 is the 2.00 liters multiplied by T2, which is the 250 Kelvin, divided by the 300 Kelvin for T1. And then we do the number crunching. So that's 2 times 250 divided by 300. And according to my calculation, this works out to be 1.67 liters. So that would be what the question is asking for. All right. Okay, so that's basically it for today. And we'll continue our discussion on Thursday. As far as assignment number, 4? I'm going to set up a Dropbox for that. And the deadline for that, I'm going to set it at Friday. So if you have any questions, of course, while you're doing it, please feel free to contact me and I'm available for you to help you guys with any difficulty that you might have, all right? Also, let me just say that I'm still in the middle of grading your tests. I've been sidetracked by other things, so it will take a while. So I expect that I'll be able to finish grading your test by the end of this week. So you should see your grades posted. And also I should be able to send you your graded work as well by email. Okay. All right, so that's it, folks.